Good afternoon, students. Today, our topic is Gauss's law. This is one of the, you can say, a very difficult part of physics. And in class 11, 12, from class 11, if you remember, rotational mechanics is one of the most difficult part. And in class 12, electrostatics and Gauss's law. But one thing I can tell you, if you remember the basic concept, and you know how trickily you can apply them, then the problems becomes very easy. Let us see. We will just jot down what we have studied in Gauss's law, right? And we'll move on to solving problems. Okay. So what does Gauss's law says? With the help of Gauss's law, we can easily derive electric field for any irregular conductor. Definitely, it will hold true for regular conductors also, but easily we can derive E. So what does Gauss's law says? It says that the electric flux through a conductor, right, is nothing but the integral of electric field, right? This is nothing but the charge inside the conductor enclosed within the conductor divided by epsilon 0. Now see, this is what? This is electric flux. What is electric flux? Flux is nothing but electric field into multiplied by the area. For small area we can integrate them. That will be equal to the charge inside, right, enclosed within the conductor divided by epsilon 0. Now what happens for a regular conductor where the electric field is uniform, we can just multiply E into S equals to Q in by epsilon 0. So E can be written as Q in by S by epsilon 0. Now this concept we can use it to find out the electric field for any kind of charge distribution in conductors, such as first we are going for a point charge, say a point charge Q. Let us assume a Gaussian surface, which is, for simplicity, let us consider a sphere around this point charge Q. Now what is this sphere? This we are naming as Gaussian surface. Gaussian surface is nothing but an imaginary surface which we consider to find out the electric field, right, which is coming out of the surface, right. Now say if it is positive charge, the electric field will come out, it will originate from the positive charge. If it is a negative charge, the electric field will go in. Now what we know, the electric flux associated with this surface is what? Say as the electric field is radial, it is uniform, it is E, into what is the surface? Surface area is 4 pi, say the radius is R. Say the radius is R. So E into 4 pi R square is equal to Q by epsilon 0. So E becomes what? 1 by 4 pi epsilon 0, right, into Q by R square, which you have already deduced using principle of electrostatics, right. Now this is for a point charge. Now what if a charge is distributed throughout this whole line? If it is a linear charge distribution, say lambda is the linear charge density. Got it? Now say this length is L. This length is L, so definitely the Q, the charge Q will be what? Lambda into L. Say we are taking a Gaussian surface which is just like a cylinder, then what will happen? The charge, the electric field is coming out like this, right? See, this radius, say we are trying to find out what is the electric field at a distance of r. So at a distance of r, we are considering a cylinder, right? Now, if this is r, then what happens? This perimeter is 2 pi r into the length L, the surface area through which the electric field is coming out. That is a surface, that is the electric flux, is nothing but, we can write E into 2 pi r into L. That will be charge, which is nothing but lambda L by epsilon 0. So L cancels out. E becomes 2 pi lambda by r. Understand? That is, electric field through a linear charge distribution is this, where lambda is the linear charge density. We can also find out similarly for a plain sheet of paper, for a plain sheet of charge distribution, right? For this plain sheet, let us consider a Gaussian surface, which is also cylindrical in shape. If you see, the electric field will be like this, right? So the surface area, that is this surface area, not the cross section, but this surface area of the cylinder is parallel to the electric field. The flux associated with this is 0. So finally we have to find out the flux associated with this, right? Now you see, electric field is coming out in this direction as well as it is going out in that direction. So if this is S0, so there is another S0 in this side. So the flux is what? E into 2S0. Now what is, say, sigma is the surface charge density, right? If this is a surface charge density, then what will happen? Then this charge Q enclosed is this into S0. Now flux will be equal to Q enclosed, write this, so SS cancels out, so as E becomes sigma by 2 epsilon 0. But interestingly, this is a plain sheet of charge, right? But if it is not a plain sheet but a plate, then what will happen? Okay, there is a question, what is QIN? QIN is the charge enclosed, is the charge enclosed within the conductor, right? Okay, now see, for a plate, for plate what happens? See, in this case, right, in this case, E into 2S. Here, the E is also, for calculation of flux, we are multiplying with 2S0. At the same time, as it is a plate, charge is residing on this surface as well as this surface. So Qin is nothing but surface charge density into 2S0 divided by epsilon 0. So here 2S0, 2S0 cancels out. E becomes sigma by epsilon 0. Okay, now we are moving on to next part, that is the properties of conductor. Now see, I have enumerated the properties of conductor. The first, what is said? It is said the excess charge on a conductor resides on its outer surface. That is, what happens, say there is a conductor. If you try to keep any charge within that, right, it will produce some electric field. Now, because of this electric field, the free electrons in the conductor will start moving. Will start moving means, right, it will form electric current. But we know, for that is, we are producing current without the application of any potential. That is, if it is like this, if electric charge resides within the conductor, it will actually violate the law of conservation of energy. That we are getting current means we are generating electric energy without the application of electric energy. So what happens? Any charge in a conductor, if there is no other electric current source, will always reside in the outer part of the conductor. Understand? Only why? Because see, if in a conductor, if charge resides outside and we take a Gaussian surface, right, electric field, what I said, electric field should be 0. Now when electric field is 0, what is flux? Flux is E into this surface area, which is also 0. So flux is equals to QIN divided by E0. If flux is 0, then QIN should be equal to 0. First. Second, electric field at any point close to the charged conductor is sigma epsilon 0. That is, say there is a charged conductor like this. What is said? Electric field will be equal to sigma epsilon 0. Let us draw a simple Gaussian surface. Now see, similarly we can say, if the charge density is sigma, so this S and this S, they are same, right? So we can say electric field, electric flux E into S0 will be equals to sigma S0 divided by epsilon 0. So S0, S0 cancels out, right? And so it shows that electric field is dependent on the surface charge density. Now what will happen? Suppose if we have a surface like this, which is much more smaller, this surface is much more broader, then definitely if surface charge density, this is sigma 1, this is sigma 2, then definitely sigma 1 will be greater than sigma 2. Therefore E1 is greater than E2. And this is I mean, with this you can understand, like all the spikes, जितना भी spikes होते हैं वहाँ पे electric field ज़्यादा form होता है. Understand? Okay. Now we are coming to the third property. The third property is electric field and field lines are normal to the surface of the conductor. Same thing. The electric field lines are normal to the surface of the conductor. Now in a conductor, if the electric field is not normal, suppose electric field is at an angle, then definitely it means one component is normal, definitely one component is normal, and another component will be parallel to the surface. It means through the surface there is electric field, so the free electrons should flow within the conductor without the application of any potential difference, which cannot be. So definitely the electric field should be normal to the surface. Got it? Okay. Now we are coming into another interesting part, that is cavity within a conductor. See, within the cavity also, suppose we have kept a charge Q, right? What will happen if you take a Gaussian surface within the conductor, right? It has enclosed the charge Q. Yes. There is a question, is it compulsory the electric field? Yes. In a conductor, if there is no current flowing, that is, we haven't applied any external electrical source, then the electric field should be 0, and that way we are also applying the in the problems of Gauss's law. That is one of the most fundamental property of conductors. See how we apply this. Say this Q, there is a Q lying within the cavity. Now see, if this is a Gaussian surface, then see the electric field within this should be 0. Electric field, if it is 0, then we know from the previous thing that the charge enclosed should be 0. If charge enclosed should be 0, what does this mean? That is, within this surface, the inner surface, a minus q charge should be induced, because then only qn will be plus q and minus q, which is 0. And if this is minus q, then to keep the conservation of charge to be constant, this is q, this is minus q, this surface should generate a plus q charge. This surface will generate a plus q charge. And what will happen? The electric field will be 0 within the conductor, and it will be only lying in the outer region, right? And that is why this and there is no electric field inside. Inside, you see this positive q is generating one electric field, which is originating from the positive q. This negative q, the electric field is directed inside. So what is happening? This electric field and this electric field vectors, they are cancelling one another. So electric field within the cavity, electric field in cavity becomes 0. This property is used for electrical shielding. Right? Electrical shielding means, suppose we want to protect any very sensitive electrical instrument. What we do, we make a covering of conductor, and we keep this electrical instrument within the cavity, right? So no external electric field can influence this one. Okay, now let us solve 2-3 problems. Okay, say a point charge q is placed at the center of a cube. What is the flux linked with all the faces of the cube? In a cube, how many faces are there? It is definitely 6 faces. Now, what is the flux linked? The flux linked should be charge encloses q divided by epsilon 0. This will be the total flux linked. Now, what is the flux link with each face of the cube? Now, with each face of the cube, what will be the flux linked? There are 6 faces, and it is uniform. So flux linked in each faces will be q by 6 epsilon 0. If charge is not at the center, then what will be the answer of A and B? What do you think? It will be same, because it does not depend on whether the charge is lying on the center, within the center, or not. If it is enclosed, the flux will be q epsilon 0, and so we get this phase flux. Okay. Now, yes, we'll come into another problem, but before that, I want to discuss few other important things. I want to discuss the property of conductors in detail. I have enumerated those. Like I was telling about, electric field will be 0, right? Let us read this. Net charge inside a closed Gaussian surface drawn in any shell is 0. In any shell, within any shell, the net charge inside a closed Gaussian surface should be 0. Potential of the conductor, which is earth, is 0. Definitely. If we take a conductor, which is earthed, the potential at this point will be 0. If two conductors are connected, they are at the same potential. If two conductors, they are connected, their potential, if this is 1, this is 2, so V1 must be equal to V2. Charge remains constant in all conductors except those which are earthed. If it is earthed, then definitely the potential becomes 0, and then there is a charge redistribution occurs. Charge on the inner surface of the innermost shell is 0 provided no charge is kept inside it. In all other shells, charges reside on both the surfaces. Suppose we took two shells, right? We give charges. Charge on the inner surface of the innermost shell. If we provide any charge inside that we have seen, the charge will be reflected at the outer surface. So here the charge should be 0. This part the charge should be 0. The charge only resides in the innermost shell, the outer surface. Here Q1, maybe Q2 and Q3. Charge on the inner surface of the innermost shell is 0 provided no charge is kept inside it. In all the other shells, charge resides on both the surfaces. And equal and opposite charges appear on opposite faces. This also we have discussed. Like otherwise, within a conductor, if this is plus Q, this should be minus Q. Otherwise, net electric field will be within the conductor, which cannot be. So, in order to make electric field 0, this will be plus Q and this will be minus Q. They will be equal and opposite. Okay, let us see how we can use these concepts in a problem. This is a very interesting problem. Figure shows two conducting thin concentric shells of radius r and 3r. The outer shell carries a charge q. Inner shell is neutral. So inner shell, the charge, there was no charge. Find the charge that will flow from inner shell to the earth after the switch S is closed. After the switch S is closed. So what will happen to the charge? Now see, when switch S is closed, this will become, see, this is Q equal to 0, this is Q. Now see, when the switch S is closed, say this is 1, this is 2, then what will happen? The voltage at 1 is 0. Now, from voltage equations, you know what is voltage at 1? Voltage at 1 can be written as, that is, say this is Q and this is Q dash. Okay, now Q dash I can write voltage at 1 is equals to 1 by 4 pi epsilon 0 Q dash by R plus this is Q 1 by 4 pi epsilon 0 Q by 3R. Understand? So this voltage will be equal to 1 by 4 pi epsilon 0 Q dash by R plus 1 by 4 pi epsilon 0. This is Q by 3R, right? So this will be 1 by 4 pi epsilon 0 Q dash by R by Q by 3R. Now we know as it is earth, it is 0. So therefore, Q dash by R plus Q by 3R equals to 0. So now Q dash becomes minus Q by 3. Just check if there is any question. That's electrical shielding. Okay, electrical shielding. Electrical shielding, what I said, if within a conductor there is a cavity, then no electric field can be within the cavity. So if there is any sensitive instrument which need to be protected, if we keep the sensitive instrument within the cavity, then no external electric field can affect this instrument, because electric field within this conductor will be 0 as well as within the cavity that we have already discussed, right? This process is called, this process of protecting an instrument is called electrical shielding. Any more questions? Okay. Now, with the help of this Gauss's law, we will also try to see how we can use, distribute the charges. Let us see. Let us consider three concentric spheres, right? Can you give me the paper?
Same paper.
Yeah. Right. See, this is a very interesting problem. See, the problem is given, this is earthed, right? This is A, this is B, this is C, this is earthed, and this charge given, the charge given to A is Q1, and you know Q1 cannot reside within the cavity, it should reside outward, it is on the outer surface of the shell. And Q2 is given to the shell number C. Now, what will be the charges within A, B and C? This is a very important kind of problem. Say, let us see, this is Q1, this is Q2. Let us consider Q3 to be the charge on this boundary, inner surface of the shell B. This is Q4, this is Q5, right? And the outer surface is Q6. Now you can say like Q2 is already given. Q2 is already given in the shell number C. So what about Q5 and Q6? Q2 is nothing but Q5 plus Q6. Okay, now we have to find all this out. Now see, this radius is RA, this radius is RB, and this radius is RC. Now, see what we can say. This is Q1, this is Q3. Now, if you try to suppose this is the conductor B. Within this, let us try to understand conductor B. Let me try to magnify it. Conductor B, let us try to draw a Gaussian surface within the conductor B. This is B. Now Q3 is lying here and Q3 is lying here, and there is another shell. This is B, this is A. Q1 is lying in the outside of the shell A. Now if you consider this Gaussian surface, the electric field within this B will be 0. So as electric field within B is 0, then what will happen? Q1 plus Q3 should be 0. So Q3 will be equals to minus Q1. Similar conclusions you can draw for Q5 and Q4. Because if you consider a Gaussian surface at this, you will see what? See Q5, Q4, Q3, and here is Q1. So we can write Q1 plus Q3 plus Q4, Q5 equals to 0, right? Now this itself is 0. So we can also write Q4 equals to minus Q5. We also know an equation Q2 equals to Q4 Q5 plus Q6. We need to write another equation. We can write another equation because potential at VB, potential, see this VB equals to 0 because it is earthed. If VB equals to 0, what will happen? We can write VB equals to C. First, to calculate VB, we have to consider all the shells A, B and C. So VB we can say for A, what is the charge? That is Q1. But Q1, right, Q1 we are not considering RA because for B the Q1 is reflected in the outer surface. So for Q1 we have to consider radius RB, that is 1 by 4 pi epsilon 0, right? This potential equals to, yes, Q1 by B. Yes, it is Q1 by RB plus this is Q3 plus Q4, this total charge, Q3 plus Q4 by again RB plus Q5 plus Q6 by R6. Now, if this total becomes 0, if C for RA, why we have taken it as RB? Because the voltage is uniform throughout the shell. Because we are considering the voltage at B, it should be constant throughout the shell. The charge is Q1, so Q1 by RB only. These charges are Q3 and Q4, so Q3 plus Q4 by RB plus Q5 plus Q6 by RC equals to 0. So by solving all this equation, you can find the charge distribution. This kind of similar problems will come in the joint entrance, right? Gauss's law is one of the difficult, but if you understand these concepts, you will be able to solve the problems. Okay, thank you for today. Any more questions? No more questions?